Okay, so now we're almost at the end of thinking about linear models with a normal air structure. And what we're going to do in this little film, if you will, is cover what is called mixed models. And as we'll see, mixed models simply refer to models where we're going to start paying a little bit more attention to our air structure. And this is especially going to be important when we want to explicitly model and account for perhaps non-independence in the random variables that we're drawing from a population. And so as a disclaimer, I put together these videos when I naively thought that it would be easier to make a bunch of 20-minute video vignettes that I would then post. And so this is actually going to be edited together three different short videos. So if I start referring to what I did last time, I'm probably talking about what I did 2 minutes ago. Um, yeah, early on, I thought that it made sense to have a bunch of really short videos posted, but then I realized that pretty quickly there would be a YouTube channel with hundreds of videos on it, and that just seemed like that would be kind of a paper keeping mess. So, anyhow, let's go in. We'll jump in, and we will start thinking about our soon to be new friend, the linear mixed model. Hi, folks. Welcome back to my house. Um, Today, we're going to start the first of what I believe will probably be three installments on what are referred to as mixed models. And so, to start off, I have some data that we can play with, and it is saved as an R object. So here I can load it in. So it's saying loads, split a yield, and now I have this object called yields that is now in my workspace. So let's first set up the general design of this experiment. And so we're interested in the effects of either being irrigated or not irrigated, the effect of being at low, medium, and high density, and then various fertilizer combinations, nitrogen, and phosphorus. Um, and you can see here that we've done this across 4 different fields. People were nice enough to let us use their field to do these experiments. And the response variable of interest is the yield. And so what we want to know is whether or not any of these factors. And so let's start something with just a really simple thing, and let's just think about irrigation. So we could make a simple linear model where we are going to think about the effect of irrigation on yield. Okay, and this is the same kind of a linear model that we've been building now for three or 4 weeks. So we go ahead and we can do that. And there we have the parameter estimates from our linear model. This should obviously all look very familiar to everyone. And we can think about what we're actually doing when we do this. There's a box plot. Here is the control. Here is the irrigated. Again, we're interested in whether or not there's an effect of irrigation on the yield. And just by eyeballing that box plot, it looks like there probably is. And of course, as we've talked about a number of times behind the scene, what is happening is the computer is using dummy coding, and it's really looking something like this, where we have all of our data, where this would be 0 here for control, because alphabetically it becomes before irrigated, which starts with the letter I, in case that was unclear. And so here we have our control in the irrigated. And again, if we put that model, or if we put the line to the model, that's essentially what we have modeled. And that's where that's where we've been, right? We've been setting up linear models, and we've been thinking about it. But now we're going to think about something that maybe we haven't considered when thinking about our data. And so there is a certain level of non-independence that we have among the various fields, right? Because we've replicated this experiment 4 times in field A, field B, field C, and field D. And we might want to account for the fact that, first of all, that there is non-independence or relative non-independence among the different fields. That is, the random variables that we're grabbing for yield, we would expect that if you're in field A, you might be more similar to other things in field A as opposed to the samples that you're taking from field B, etc. And so this is where the concept of a mixed model comes in. And mixed models are often referred to as random effects models. And what we want to think about are what do we mean by a random effect? So a random effect is an effect that basically varies in a way that we don't have any control over, or that is explicitly not interesting to us in the context of hypothesis testing. And so here, field would represent a random effect, because we could imagine that those 4 fields that we have are 4 samples from a population of possible fields. It just so happens that we happen to have done it in those 4 fields. And so we would want to treat field as a random or varying effect so that we could basically account for variation that might just inherently occur among fields. You could imagine, one field might have had soybeans last year, one field might have had corn last year, another field might have been, just kind of left fallow for a couple of years before we decided to come in and do our experiment. And another field could be an old brown field. It could be an old industrial site, but we happen to be doing the experiment there. So if we want to test hypotheses about, for example, the effect of irrigation, and later we'll do the effect of density and the effect of fertilizer, what we're going to want to do is we're going to want to account for that variation among fields. And there's really kind of 2 different ways that you can think about why that might be important. The first reason why that might be important is we do want to explicitly account for the non-independence of the data that we're taking from each of those different fields. That just seems like the honest thing that we're going to want to do when we're estimating our parameters. The other reason why we might want to do it is it might actually increase our ability to detect something. And that's because up to this point, we've just been dumping all of the stuff that we do not know into the common error term. So I'm going to use my fancy new whiteboard here and think about what we have done historically. So historically, we would be interested perhaps in yield being some function of what, being some function of irrigation. Let's just call that the model for right now, because that's just a generalized statement of what we've been doing up to this point. And then we've just had an error term. And when we were doing the hypothesis testing, what were we doing? We were looking at the ratio of the variance component that our model is explaining of our data versus the variance component that we're unable to explain given our data, which is why when we calculate that F statistic, right, we take the mean squared of the model divided by the mean squared of the error, and that's how we that's how we've been calculating our F ratio. So what we're going to do in a mixed model is we're going to appreciate the fact that we actually know a little something about this error term. It's no longer junk. It's the variation that we're unable to explain in our model, but it's not variation that we totally cannot explain. So in our case here with our model, make this maybe a little bit bigger because it is a whiteboard. There we have it. So what we're going to do when we set up a mixed model is we're going to put structure to this error term. And so you could imagine, given our example here where we're trying to predict yield, that instead of just saying plus error, we're going to have the error maybe among fields, and then the leftover error. Leftover. How am I doing here, folks? Right. So now we've put some structure to our error term, where we have the error among fields, which is what that spells, even though it looks like it said Phelps. We have the error portion that's among fields, and then we'll also have the error that's still the leftover residual thing, or residual term. And the way that you can think about how this might increase our statistical power to detect an effect is that if there is a lot of variation among fields, and if all we're doing is setting up a simple linear model, we're taking that point estimate across all fields, if there is quite a bit of variation among fields, we're going to have a lot of variance that is going to be unexplained, because you're going to have a lot of points that are far away from that grand mean. If we can get rid of the among field component portion of the variation, now we'll have less error that we truly have not accounted for and that we can't explain. And we could imagine a scenario where then if we look at the ratio of really what we can't explain left over versus what we can explain in our model, that we're going to have increased power. And so this is what is referred to as a random effects model or a mixed model. Okay, and so let's go back and think about for a moment what we're doing here with our data. Oh, and I will mention that this type of a design where we've redone this experiment 4 different times, essentially across all of those fields, is what's often referred to as a blocked design. And so each block here, each field, is receiving all of the possible treatment combinations. Okay, and so if we think about it, let's go back and we're looking at our yields there, but I'm going to just go ahead and think about what we might be interested in doing. So here, get me out of there. Get me out of there. Come on. Oh, there we have it. So here I've made a box plot where this is field A, control and irrigated. This is field B, control and irrigated. Field C, and field D. Okay. Again, the hypothesis that we're interested in at this point is whether or not there's a difference between control and irrigated. And we can see that overall it looks like within each of those fields, control is always less than irrigated. But note that there is some evidence, just by eyeballing this, that there is a difference among fields. So field A overall just appears to have lower yield compared to fields B, C, and D. And that's the portion of the variation that we are going to want to account for when we're setting it up as a mixed model. And so let me make that small again. Bye, figure. Bye. Okay. Ooh, look at all these warnings. Okay. And so how we're going to set up a mixed model, and there are 2 primary packages that are in R that people use to set up mixed models. I'm going to use the one that everyone has kind of gone to. If you look at an earlier books or older books, I believe it was called ADE4, which was a model for doing random effects models, whereas we're going to use what's called LME4, which is what I would say 95% of people use now for mixed models. I just wanted to mention that the other package exists because some older tutorials online and some older books might have, they might be using the different package. And the syntax is different, and it seems like a waste of time for us to learn the syntax of 2 different libraries when everyone is using LME4. So we would say library LME4, going to load that in. And so the first thing I can do is I could try to make a model. So let's call it mod because I tend to like calling things mod. And now since we're going to do a mixed effects model, we're not going to use LM as the function. We're going to use LMER. Elmer is what often the kids refer to it as, Elmer. So we're going to set up an Elmer where again we're going to have a yield as being some function of irrigation. And then our data again will be yields. So what I've done right here is I have typed the identical model that we had up here with using the LM function as a linear model. Here I'm doing it as an Elmer. If I run that, I will get an error message, and the error is that there's no random effect specified in the formula. So we're going to have to tell it what we want the random effect to be based on. In our case, what we're going to do is we're going to put field in there, because we're going to assume that field is the random effect. And again, we can think about the reason why we're treating field as a random effect is because those 4 fields were sampled from a population of possible fields. And again, we can assume that there might be differences among fields, just inherent differences among fields, and we're going to want to account for that portion of the error. And so the first way, or the first thing that we can do is we can assume that the treatments might have an effect across fields. But let's assume that each field has its own intercept. And by its own intercept, what are we saying? Again, if we think about how dummy coding and stuff works, we're going to assume that each field has its own baseline for the effect of the control treatment. Because we know that alphabetically control is going to come again before irrigation. And what we're going to do then is we're going to think that each field has its own baseline. So that way when we generate a parameter to think about the effect of irrigation, we can think about it as all being kind of scaled or relative to a different intercept for each field. And so how we do this in the LME4 package is we tell it that we want each field to have its own intercept. And we do that by saying one pipe field. Okay. And so what this piece of syntax right here is telling us, or telling R, is that we would like to model this as a mixed effects model, and we would like each field to have its own intercept. And this is how we will account for that, or for that random effect. So I will go ahead and say mod. Now I don't get an error message because I have put this term in there, and we can go ahead and let's take a look at our mod. Okay, so here is our mod. Notice that now the output is slightly different than when we had just a straight up linear model and we looked at the summary. We still have the information that's included up here, which is what our formula was. And now we have these random effects portions. And the random effects portion, this is the variance of the error term here that is explained among fields. And then here is the variance that's left over. And so we've gone from a model where we've basically been able to cut in half the amount of variation that we cannot capture with our model. Let's compare that to our simple linear model, and we can see what some of the differences and what some of the similarities might be. Nice. Okay, so that's our linear model. And then that is our mixed model. And so here's our straight up linear model, right? No random effects in this model. And notice that we have, again, our intercept, and then we have the effect of being irrigated. So on average, you would expect if you're irrigated, the yield is going to be 21.4 greater than if you were not irrigated. And if you were not irrigated, that's the expected amount, right? We already understand how we can interpret those parameters. If we go down to our mixed model, note that the parameter estimates are the same. So the magnitude of the difference is the same. The model is still capturing that. What has changed, however, though, is the uncertainty around those parameter estimates. So here, notice that we have a standard error of 3.4 around the intercept, whereas when we set it up as a mixed model, we have a standard error of 8.598. So why might that be? When we did it as a simple linear model and we weren't accounting for the among field component, we had a lot more information for that parameter estimate, right? Because we assumed that they were all random variables drawn from the same thing. As you increase your sample size, you're going to decrease the standard deviation. All the standard error is the standard deviation around your estimate of the mean, which is the intercept. And so by setting it up as a random effects model or as a mixed model, we've actually increased slightly the uncertainty around our parameter estimate for the intercept. However, in this case, if we look at what's happening to the uncertainty around our estimate for the slope, in our standard linear model, the standard error is 4.926, and in the mixed model, it's 3.56. So we've actually decreased the uncertainty around our slope estimate. And why might that be? Well, the reason why that might be is that there was an inherent difference among the different fields. And that means that we had a lot more spread around all of those, around that slope when we put a single slope there. By removing the variation among fields, we've actually decreased the uncertainty around our slope estimate. And in principle, then, we might have, as a consequence, increased our statistical power to detect an effect. One other thing I want to mention here is this part right up here where it says it's a linear mixed model fit by REML, R-E-M-L. And what REML is, where is my, oh no, already lost it? God. Okay. REML stands for a number of different things, but they all have the same acronym and they all essentially mean the same thing. The ML part stands for maximum likelihood. So that's good. Maximum likelihood. Okay? The R part of that can stand for one of two things. It can either stand for residual or restricted. Either of those are totally fine terms that we might decide we want to use to describe what REML is. So what is it? That's a good question to start with. What it refers to is that when partitioning the error structure, when we're setting up a model, a mixed model, it is using maximum likelihood to estimate the parameters associated with the error term, but then once it establishes the error term using maximum likelihood, then the rest of the model is done just as we've been doing linear models since we began, which is ordinary least squares. And so we're only restricting maximum likelihood to the error component of our model. And so why might we do that? We know that maximum likelihood estimates are always going to be biased. And they're going to be biased because the observed data is always going to be closer to the parameter estimates based upon the observed data than the true population data. So for example, the maximum likelihood estimate for the standard deviation, those are always going, all of those data points that are used to calculate the variance are going to be closer to our estimate of the mean than the true population mean. And if you remember way back early on, that's one of the reasons why we have that n-1 in the denominator when we calculate the variance. It's to get rid of that particular bias. And so what REML then is doing is it's using maximum likelihood for the error term, and then the rest of the model is being done kind of as a standard as a standard ordinary least squares. There is an argument within the Elmer function that you could actually say REML equals false, I believe. Let's see here, question mark, Elmer. Let's take a look-see here. Right here, there is an argument, REML equals, if you had said REML equals false, then it would fit the entire model using maximum likelihood. And again, we'd rather not do that because even though maximum likelihood sounds a little bit more fancy, we know that it would be biased, and we'd like to have the best unbiased estimator that we could possibly have. Okay. And so we could even look here. Let's go back to where we can look at things and see what REML did, right? So here's our REML. Here's our random effects again. Here's our fixed effects. And if I were to use this function called coef, which will give me the coefficients, here we can see here are the different intercepts, because again what we did is we allowed each field to have its own intercept, so its own baseline, and these are the means within the group. So here again, here's that field A, which always looked like it was underperforming compared to the other three fields. And here are, here's field B, field C, field D, etc. And so this is what it was being estimated using the maximum likelihood portion of it. These are our different intercepts. That's the part of the error term that we are putting structure to. So it's not that we don't know what's causing some of that variation. We just don't necessarily care in the context of hypothesis testing. So we want to account for it, but we're not necessarily doing hypothesis testing on it. And as a consequence, that's why we're using the general linear mixed modeling approach. Okay, so one other thing that I will mention is that there could be a scenario where you would not treat field as a random effect. So don't always assume that fields or growth chambers or whatever they might be, anything that you would block by, don't always assume that they have to necessarily be random effects. So one scenario here where you would want to treat field as a fixed effect is, imagine you were hired as a consultant by somebody who was going to buy a field, and they were going to buy one of these 4 fields, and they wanted you to do the experiment to find maybe the best field, the one that has the greatest yield, et cetera, et cetera. In that case, you would want to include field as a fixed effect because you would actually be interested in variation among the fields. Whereas in the scenario that we're doing right now, we are assuming that the field is just not nuisance, but just a random effect that we don't really have that much control over. Okay, so that ends this little part. What we've done is we've set up a very simple mixed model. We understand why we did that and what what we're doing by allowing each field to have its own intercept. So what we'll do next time is start thinking about hypothesis testing, because I don't know if you noticed, but there is no p-value here when we did summary, right? We got a t-value, no p-value, whereas with our standard linear model, we get a t-value and a p-value. So what we'll do next time is we'll talk a little bit about the hypothesis testing part. Okay, everyone, welcome back. We're going to keep talking a little bit about mixed models here. So let me make myself small. And I'll make myself really small, and I will hang out down there in the corner. So just to remind ourselves of where we are at, we had these data called yields. And within yields, we had what? Well, we were interested in determining whether or not these different factors, irrigation, density, and fertilizer, somehow influence yield. And what we've been playing with thus far is just a simple model where we're only including irrigation in the model. We're ignoring the fertilizer and the density treatment. But then we also conducted this experiment across 4 fields. And what we decided to do last time was we were going to treat fields as a random or varying effect. Largely because we want to account for the fact that there could be differences among the fields that we don't have any control over, whereas for example, with like irrigation, we have control over that. So we would call that a fixed effect. With field, we can consider it a random effect. We also might want to think of them as being a random effect because the fields themselves are basically 4 draws from a possible population of fields that we could have done the experiment. We just happen to use these 4 different fields. And so we wanted to account for differences that might just be evident across those 4 different fields that have nothing to do with our treatments, but they can certainly affect the variance estimates around our parameters. So we're going to control for that by putting some structure to the error part of our model. And we did that using the Elmer function from the LME4 package. And using this syntax here, this is how we asked R very kindly if it would be so kind as to give each field its own intercept. So we're going to allow the baseline of each field to be different, so that way we can actually go ahead and do the hypothesis testing on our fixed effects while controlling for all of that variation that we don't necessarily care about, but we can certainly model, since we know that some of that error or residual variation will be explained just simply because there's going to be variation among fields. And so when we finished off, we did this, we ran our model, and we looked at the summary of the model, and I pointed out that there is no p-value associated with these fixed effects. And in fact, if we were to use the ANOVA function, the built-in ANOVA function, we'd see that we get what they're calling an analysis of variance table, but it's not providing us with all of the information that we're used to seeing in a ANOVA table. In particular, we are not getting any information about what's happening in the residual variation. And that's because there's no generally universally accepted way to do hypothesis testing on a mixed model. There's actually a number of different methods, and all of them could be argued that they are fine and they are appropriate, but there's not a single best way to do it. And the authors of R, I'm assuming, didn't want to get into that argument with a bunch of statisticians, so they decided to provide as much information as possible without doing the actual hypothesis testing. And so, but we want to do the hypothesis testing. Right now we have a model where we have irrigation in the model, and we'd like to know whether or not irrigation should be included in that model or not. If it should be included in that model, then that would mean that the irrigation treatment would be significant. And if it weren't significant, that means the best that we could do is just calculate a grand mean. And so I'm going to go over today briefly 3 different ways in which we can do hypothesis testing when dealing with mixed models. 2 of them are pretty similar to one another, and one of them is a little different, but it might be more familiar to you because it actually does put it into an analysis of variance framework. And so why is it that there's no agreement as to how to do the hypothesis testing on a mixed model? And it all comes down to there is no general agreement as to what the appropriate degrees of freedom should be. Because remember, when we do a standard ANOVA, that the degrees of freedom in the denominator are the residual degrees of freedom, and that's the leftover random variables that we have after we calculate, the grand mean and all of our other parameter estimates. Because we've put structure into the error term using maximum likelihood, we don't really have, there is no agreed upon degrees of freedom for the denominator, and hence we have to come up with other ways of thinking about that. So the first way that we can deal with hypothesis testing is to do what's called a likelihood ratio test. And a likelihood ratio test, as the name implies, looks at the ratio of 2 likelihoods of 2 models, and then it asks whether or not that ratio is bigger, or if those models are significantly different from one another. And the general setup for a likelihood ratio test, I'll use my fancy whiteboard here, is we would start with the likelihood of what we'll call a null model divided by the likelihood of what we can call the full model. Okay? And we'll turn that into log because we like to deal with logs. And then we will multiply that by -2. And what that's going to calculate, that -2, whenever you're multiplying that by a log likelihood, that's creating what's called the deviance of the model. In principle, this should be distributed as, it should be chi-squared distributed. And so if we wanted to compare those two, what we can do is we can take these 2 models. So here I have the mod full and I have the mod null. Since we're going to be extracting the likelihoods out of that, we can go ahead and say REML equals false. So granted, oh no, I don't want to type it there. Come on, get it together, Jim. Let's see here. What? Killing me. There you go. And so I'm saying REML equals false. That way the entire model itself is based upon the log likelihood. And then I can, or the whole model is based upon a maximum likelihood estimation. So we know that the parameter estimates are going to be biased, but this is the only way that we can extract the true likelihood out of the model, is to do the entire model playing by the same rules using a maximum likelihood approach. And so here I have mod full and mod null. And so again, here's the model, here's the parameter estimates that we saw before for the full model. For the null model, all we have is an estimate for the grand mean. And so here's our 2 different models. And I want to point out that the null model is actually nested within the full model, right? So it's a nested structure where, if you recall, like when we were using AIC, we could compare all kinds of different models, and they didn't necessarily have to include any of the subset of the same predictors. With a likelihood ratio test, our full model is one that includes all the parameters of interest at that moment, and then our null model is the one that doesn't include those parameters, but it doesn't include any other additional parameters. So whereas in AIC, you could compare, say in this example here, a model that just has irrigation and a model that just has density, you can't do that with a likelihood ratio test. The likelihood ratio test is always going to be something where it's a nested structure of how the models are put together. And so now I have these two models, and as we've played with a little bit before, is that we can extract the log likelihood. Log dot like, oh, it's just log like of what? Of our mod full, what, killing me, oh, this has to be capital H, okay. And so there is the log likelihood of the full model. And then similarly, we can extract the log likelihood of the null model. Okay, so now we have two likelihoods. Our null model is negative, up here would be negative 317.48, and down here would be negative 302.773. So we could look at the ratio between those two, and I will do that. I will copy and I will paste. Here I'm putting this little bracket 1, so it's just extracting that value for the likelihood, so I don't have to deal with those degrees of freedom. So we can go ahead and we can do that, and now we have, that is that ratio. And so now if we were to take that value, negative 2 times the log of that ratio, we get 29.43083. We could then take that number and we could compare it against a chi-squared distribution. How we determine the appropriate degrees of freedom doing a likelihood ratio test, the appropriate degrees of freedom that we will use for the likelihood for the chi-squared distribution is going to be the difference in the number of free parameters between the two models. And so if we went back here, the full model, it's telling us that we have 4 degrees of freedom. And it's telling us we have 4 degrees of freedom because we've estimated an intercept, we've estimated a slope for the effective irrigation, and then we've also estimated 2 different groups of parameters for the error term. We have one that describes the among fields component, which is our random effect, and then we still have all the leftover variation. And then for our null model, all we've done is the grand mean, and then again our 2 different components of the error structure. The actual values of those degrees of freedom don't matter. What matters is the difference in the degrees of freedom between the 2 models. So in this case here, we would have 1 degree of freedom. So we would go and we would look at the cumulative distribution function for a chi-squared distribution. That would be the value with 1 degree of freedom. Okay. I will point out, just in case it was confusing you, why I put that exp there, and that's because the log-like function extracts the log likelihood, and if I want to use this math here, I don't want the log likelihood, I want the likelihood, so I had to exponentiate those values. This is the exact same thing as if we were to simply take the log likelihoods. So we got, here's the log likelihood for the null model, and then here is the log likelihood for the full model. Recall that when we're in log land, those things that we otherwise would divide, we now subtract. So we'll take the log likelihood of the null model minus the log likelihood of the full model. We'll take that value and we will multiply it by -2. And that is going to give us the same answer as we got when we did it the long way. So this is usually the standard way of doing it, because usually we're extracting the log likelihood because the actual likelihoods end up being super small numbers, and we end up starting to have all those problems that we have with floating point problems and rounding errors in the computer. So we stick with log. Plus it's easier to subtract than it is to divide big giant numbers. Okay, so built into R, we can do this without doing all of that math, right? Without doing this, and we can use that lowercase ANOVA function. And that lowercase ANOVA function, if we were to give it 2 models, we'll give it our null model, and then we're going to give it our full model. What it will do is it will do the likelihood ratio test for us. So I go ahead and I do that. And right here is the chi-squared statistic that we generated up here. same number is up here, is the same number that R is giving us here. That's good. That means that we're doing the arithmetic correctly. And then again, it's looking at a chi-square distribution with 1 degree of freedom, and the p-value is 5.7 times 10 to the negative 8th. So if our alpha is 0.05, we feel pretty good saying that irrigation is significant and it should remain in the model. If we had not said REML equals false, just to kind of illustrate something, case. So I'm going to go ahead and do that. Now I have fit both those models using restricted maximum likelihood or residual maximum likelihood, where we're only using the likelihood for the error structure, but we're not using the likelihood for the fixed part of the model. If I then were to compare those models, we will get this announcement from R that it's telling us that it's going to refit those models using ML. So R will do that automatically for you if you're using the lowercase ANOVA function to do a likelihood ratio test comparing two models. I point that out because in older books and in older tutorials, you had to have that argument in there saying REML equals false when you were comparing two models. But now R does it automatically for you, and it just lets you know that it's refitting those two models. And so that is one very valid way that you could do hypothesis testing then on this mixed model. So we would walk away from this and we would say irrigation appears to be important. Chi-squared is 29.43, degrees of freedom is 1, p is less than 0.05, or we could say 0.057, whatever. I guess it'd be a lot of zeros than a 5.7. Okay, so that is the likelihood ratio approach. So there's a slightly different variation of the likelihood ratio approach, which is called a Welch chi-squared test. And it is very, very similar to the likelihood ratio, except it also is including a little bit of information criterion in it behind the scenes. I'm not going to even bother showing the math on it. It's not terribly exciting, and at the end of the day, you're still going to get something that you're going to compare against a chi-squared distribution to test for statistical significance. The easy way to do the Welch one is to use that package CAR that we've been using, the one that is very kind, and it gives us the marginal sums, p-values and f-ratios based upon the marginal sums of squares. If we were to use that exact same function with an Elmer object, which is the mixed model object, and if we were to put our full model into the ANOVA function, we get an analysis of deviance, type 2 Wald chi-square test. Here is our chi-squared value, and then here are our p-values. Notice that they're not exactly the same between the likelihood ratio and the Wald approach. The Wald approach tends to have a lower p-value because it tends to have a higher chi-squared. There are no real general rules of thumb, frustratingly, as to what the best is. I often use the capital ANOVA function just because it's convenient, because I don't have to type out the full model and the reduced model and then compare the two using the lowercase ANOVA function. The capital ANOVA function just seems to be a little bit, it's just more efficient time-wise. There are some people who advocate using the likelihood ratio test when you have relatively small sample sizes. Unfortunately, there's no real rule as to what defines a relatively small sample size. In our example here, we have 20 replicates per field, so I would kind of feel as though it's probably small. But there's no magical cutoff as to what is small and what is big. And like I said, I usually use the capital ANOVA function. Okay, so those are the two kind of likelihood ratio type approaches that we might consider. Oh, and I'll also say that there would be nothing wrong with is it capital AIC or is it lowercase AIC? Oh, yeah, it is. There would actually be nothing wrong with just using AIC to compare the two models. Here we see that the full model has a lower AIC score, so it's the better model. that's entirely fine, but there's no hypothesis testing involved with that. And if you're going into an analysis where you're going to do null hypothesis testing, you kind of really need that p-value. If you're just interested in comparing the two models and saying what model you think is better, if you want to come up with some kind of prediction or look at the parameter values, you could probably go ahead and use the AIC. Certainly, it wouldn't be wrong. Unfortunately, a lot of people in the universe that review scientific literature might not have enough statistical savvy to know that that's actually a totally fine thing to do. So when it comes to hypothesis testing, you can't use AIC, but if you just wanted to compare models, there is nothing wrong with using the AIC. I just wanted to mention that since we are playing around with we're playing around with likelihoods, and AIC is obviously something that we can always extract out of a likelihood. Okay, so the third way in which we can do hypothesis testing will look more familiar to everyone. And what we're going to have to do is we're going to have to load in a new library called Elmer Test. And so I'm going to load in this library called Elmer Test. And I want to point out that it's telling me that it's masking certain things. It's masking the Elmer function from the LME4 package, meaning that there's another function that's called Elmer that's in Elmer Test that will do roughly the same thing, but it's a slightly different type of an object. And then it's also overwriting the step function from the base stats package. And, spoiler alert, we're going to use that in the future because that's going to be something that's going to tell us about stepwise model selection. We're going to be able to use that in this mixed modeling framework if we use Elmer Test. So I'm kind of a big fan of Elmer Test. I just stumbled across it a couple of years ago, and I kind of like how it behaves. But so since we have, I'm going to go back up here and I'm going to cut and paste this. I'm going to have to rerun this model using the Elmer function again, because right now my version of this model was created by the LME4 package, and now when I run it again, now it's being created by the Elmer Test package. And you can see that everything pretty much looks the same. The only difference is that here it's saying it's fit by REML using it's an Elmer mod object, whereas here it's an Elmer mod Elmer Test object. And it just has slightly different pieces of information that behind the scenes the computer program is using. And so once I've created that, I can now do an ANOVA on the model. And notice now this looks more like our familiar ANOVA table. This looks somewhat familiar. What we have is the hypothesis testing on the effective irrigation. If we look here at the F value and the P, or if we look at the P value, it's very, very similar in orders of magnitude being small to both the likelihood ratio and the Welch likelihood ratio variant of that. But we have an actual p-value that's set up in the framework of an ANOVA table. So we could say, irrigation is an important effect. Numerator degrees of freedom is 1. Denominator degrees of freedom is 67. And there's our F value and there's our P value. And so this is much more similar to the traditional method of doing mixed models. And by traditional method, I mean before we all had pretty fast machines readily available to us in the form of a computer that we would be able to do the hypothesis testing on. So let's talk about we can do one more thing since we got time. Let's think about the old school way of doing things. The old school way of doing things, before we were using REML, or restricted maximum likelihood for the error term, would have been to simply put field in the model. And I will call this old school. And so with that, we could do Still want to do marginal sums of squares. But this is the type of output we would get way back in those days, which is just to put it in there as a fixed effect. I point out that here is identical to what we had when we used the Elmer test function up here. Okay, we're getting the exact same F value and the exact same P value. And that's why I said this is the more traditional method. This deviates slightly from the more traditional method when we start building models that have a much more complex error structure, which we'll get to in our next discussion. Okay, yeah, and so that's the old way, and we got 3 new ways. Again, using the Elmer test ANOVA function might just make you more comfortable just because it looks like a familiar ANOVA table, and there's nothing wrong with doing that method. Again, most people either use that method or they use either an analysis of deviance or a likelihood ratio test. I figured it was important to mention all 3 of those because they're roughly equally as common in the primary literature. So there isn't any evidence out there yet that there's a one favored method over the other. Okay, so now we know a little bit about doing hypothesis testing on a mixed model. And when we come back in the future, we'll make slightly more complex models and maybe more complex error structures. And then we'll talk a little bit about model selection, and then we should be ready to play around a little bit with mixed models. So on that, stay safe, stay healthy. I'll talk to you all soon. Hello, welcome back as we continue to discuss the wonders of mixed models. Just to remind ourselves where we're at. We decided that we were going to put structure into our error term. So in this case here, we have this object called yields. Where is it? Yields. And we're interested in knowing whether or not irrigation, density, or fertilizer plays any role in the amount of yields that we're getting. And we replicated this experiment 4 different times, essentially. We did it across 4 different fields, so these are 4 different blocks. And what we did is we set up a model where we had, right here, where we allowed the intercept, the baseline, essentially, for each field to be different. And so, again, what we're doing is we're adding structure to our error term, because even though historically we've always thought about the error as being that part that we either don't care about or that part that we can't explain, it turns out we can explain maybe a little bit of that variation by allowing each field to be different, to add structure to that error term. And we did that here by saying we would like each field to have its own intercept, and then we could compare that against a model where we don't include irrigation. So I'm going to call that mod null. So now I have 2 different models. There's one that has the a slope estimate for the effect of irrigation right here, and whereas our mod null, all we've done here is we have added structure to the error term, but we haven't put any fixed effects in the model to do the hypothesis testing on. And then if we recall, there's 3 different ways in which we can do the hypothesis testing, or at least 3 different ways that we talked about last time. One is to use the lowercase ANOVA function that is part of the base R package. If we were to give that 2 models, here I'm giving it our null model and our full model. If we were to give it that, it would do a likelihood ratio test for us. And what that's telling us is that the full model, or just our model in this case, is the superior model. That is a way to say that irrigation is significant. It's important and it's appropriate for us to model our data using irrigation as an effect. If if we were to use the capital A ANOVA function from the CAR package, it does something very similar. The one advantage of the capital A ANOVA function over the lowercase ANOVA function is that you don't have to include the reduced model. It'll do that for you automatically. And then finally, the last way is if we had loaded in the Elmer test package and we used the lowercase ANOVA function, it's no longer the lowercase ANOVA function that we're used to. R will recognize it as being something that we want to do the ANOVA using the Elmer test ANOVA function, and it does more of a traditional method of doing the hypothesis testing, where here again we're gonna reject the null hypothesis that there's no effect of irrigation and accept the alternative that there is some effect of irrigation. And so that's where we ended up last time. And again, all we're doing is we're adding structure to the error term. And so if we were to look at the summary of our model, the parameters are familiar. How we would go about interpreting them is familiar. It's similar to a normal or a fixed effect ANOVA. Again, in the random effects portion here, that's where we've added some structure to the error term. And in fact, we could say, well, given all of that error, how much of that residual variation is actually explained by fields as opposed to still unable to be explained. And we could do that by just taking these variance components and say 270.4 divided by 228.1 plus like so. Go ahead and do that. So basically we're, of all of that error variation that we had, by putting that random intercept term in there, we're explaining 54% of the variation that before we would have just dumped into the error term, which obviously then is going to increase our statistical power when we do the hypothesis testing, because now the denominator term is, it'll end up being a smaller number because there's less unexplained variation in our model. And just as a picture of what we're doing, we can look at the coefficients from that model first. Let's go ahead and do that. I will do that right now. Yes, I will. Coefficients of the model. Okay, so this is the different intercepts that each of the fields had. So each field is receiving its own intercept. Notice that they all have the same slope. So they all have the same effect of being irrigated. It's just starting at a different baseline. And so now, as a picture to see what we're doing, it looks something like this, right? And so here again is our dummy coding about being not irrigated or being irrigated. And then each of these lines here indicates the effect of each different field. And so this is the first field here, the red one. That would be field A, which was overall just had lower yields. And so we've removed that. Okay, and so there's we can add, or we could test a model where perhaps we even add more terms into the error structure to even try to do a better job at describing the error structure. And we can do that by allowing not only each field to have its own intercept, but also allowing each field to have its own slope. And so I can go ahead and I can cut and paste because that's a lot faster than me typing. Okay, and so now I'm saying I want yield to be some function of irrigation, but now I have in front of that pipe symbol right here, I've put irrigation. So what that's telling Elmer is that I would like each field to have its own intercept, but I also am willing to allow each field to have its own slope. So the overall, the amount of effect that irrigation has. And so if I go ahead and I run that, let me open up this window a little bit here. I go ahead and I run that, and let me do it again because I'm getting that normal annoying error here. But notice that I get a warning message that says boundary singular fit. And what that means, well, the first thing that means is that if you get that singular fit, that means that you are providing an overly complex model, meaning that we're trying to basically do too much given the data that we have at hand. So we're trying to put too much structure into the error term. And if we look at that model, and it's just a warning, it's not an error, so it's not necessarily wrong, it's just probably not the best solution. And if we were to look at the summary of that mod 2, notice that up here where the random effects are, we have, of course, for each field we have an intercept, and then we also have now each has its own slope. But notice that the correlation between the intercept and the slope is 1. And what that means is that R settled on a solution where it basically simultaneously estimated both the slope and the intercept, and they were perfectly correlated. So there was not a unique solution for the slope and the intercept. And again, that singularity warning is telling us that we've pretty much over-parameterized what we're trying to do with the error structure. There's no reason to have a separate parameter for the slope or the error slope for the effective irrigation, as well as a different intercept, if the solution for them is perfectly correlated with one another. And if we were to look at the coefficients for that model, coef mod 2, okay, notice now that each field does indeed have its own slope, but what I've done is if I put those numbers into a vector, so here I'm going to see how well the intercept is correlated with the slopes by just using our old friend, the core function. Here, indeed, the correlation is 1. And so it's basically, they're not able to be independently estimated. And again, that's telling us that we probably don't want that in there. But we could look and see what this looks like again. So that's when it looked like when we just had a random intercept model, but we didn't have a random slope model. And I can go ahead, and that's what it looks like when I allow the slopes to vary. So you can see that the slopes are slightly different. It looks like, the effect is slightly different in field A compared to how it is in slope B. But again, they're perfectly correlated with one another, so there's probably no reason to retain that in our model. We could similarly use a built-in function that is part of the Elmer test, which overwrote the older one, which is the step function. And we can use the step function just like we've used step functions before to assist us in model selection. And so I'll go ahead and I'll say step mod 2, and I go ahead and I run that. And let me open this up so we can see it a little bit better. Okay. So first thing it's doing is it's settling on what the appropriate error structure should be, and then it's dealing with what the appropriate fixed effects should be, and it's settling on this model, which is the same model that we were playing with before. What the step function will do, the Elmer test step function will do, is it'll do things in that order. And that being, first figure out the simplest error structure where you can uniquely identify or uniquely estimate all the parameters of your error structure. And then once you have your error structure figured out, then it goes ahead and it works on figuring out what fixed effects should be in there. Okay, good. So let's go back and look at our data that we're playing with here, actually. So here's yields, and remind ourselves that we had more than just irrigation that could potentially be in the model. We also manipulated density, and we also manipulated fertilizer. So those are all other fixed effects that, since we did the experiment, we probably would want to do we would want to probably include in the model to do the hypothesis testing on. And so what I can start with is I can start with a big, giant, super fat model. And by a big, giant, super fat model, what do I mean? Well, I'll cut and paste it, and I'll show you what I mean. There we have it. So now here's our really big fat, super fat model. So yield is some function of irrigation, density, and fertilizer. I'm also including those asterisks in there, which means that I'm going to allow for all the possible interactions. So the three-way interaction between irrigation, density, and fertilizer, as well as all the different two-way interactions. So density by, or irrigation by density, irrigation by fertilizer, and density by fertilizer. And then the reason why I'm calling this my super fat model is that I'm also just going to go crazy here with the error structure, where I'm going to allow each field to have a different slope for fertilizer, a different slope for density, and a different slope for irrigation. And so I can go ahead and I will run my super fat model. Let's run that. Here's my super fat model. And again, what you see here is we get this singular fit warning. And we also get all these other warnings that we always get whenever I have an extra monitor hooked up to my computer for some reason. But here again, it's saying we might have a problem. There's a singular fit, meaning that the internal workings of the computer could not come up with an independent solution for all of those different slopes and the intercept in the error term. And so what we could do then is we could again use our friend the step function to help us do a little bit of model selection. So I'm going to say step super fat mod. And I'm going to do that, and I'm going to get all these warnings as it's going through there saying it's not happy. And so what do I end up with? All right. And so in the end, what I end up with is an error structure that each field will get its own intercept and will also allow the slopes among those fields to vary as a function of irrigation. Now remember when we did the simpler model, where irrigation was the only predictor in the model, that was considered too fat of a model. It couldn't independently estimate those parameters. However, after we've added in irrigation, density, and fertilizer, now we have a situation where we can uniquely estimate the effect of irrigation across those fields. So we're going to end up now, what the step function is telling us is that the best model that we have is one that has both a random slope and a random intercept and a random slope for irrigation. So let's go back and see what the step function did. The first thing that the step function did was it figured out what the random effects were in the model. So again, this is the suggested approach to dealing with mixed models, is first figure out your error structure. After you've got your error structure figured out, then go ahead and figure out what your what fixed effects should be in your model. And so again, what we've ended up with here is a model where irrigation, density, and fertilizer are all in the model. We're going to allow each field to have its own intercept, and we're going to allow the slopes to vary as a function of what field that they're, as a function of whether or not you're irrigated across fields. And then it's also saying that we should have these different interaction terms in there, that we also want an irrigation by density interaction and an irrigation by fertilizer interaction. So we would have gotten the same answer had we just done it as kind of two separate approaches. So as I mentioned, the accepted approach is to first do your error structure and then do your fixed effects. So I'm going to do just the error term. So I'm going to create an object here where it's going to be called error super fat model. And why are people bothering me? Go away. All of you. Okay. So I'm going to have a super fat model just for the error structure, where I'm going to allow fertilizer to have a different slope for each field, and each field to have a different slope for the effect of density, and for each field to have a different slope for the effect of irrigation. And I can go ahead and I can run that, and again, it's going to give me this warning message. Hey, it looks like you got what we might want to call a singular fit. And let's go ahead and look at that model. And again, here's all of those correlations, right? They're perfectly correlated with one another. And again, that's telling us that the computer was unable to come up with a unique solution. So if I were to use the step function on my error super fat model, get all the warnings, and then after the warnings get out of the way, what do we end up with at the very end? We end up with the best model being one that allows each field to have its own intercept and slope as a function of irrigation. That's the same thing we did when we stuck the superfat model into the step function. And so but since we're proving to ourselves that this is how it's working, now we have our best model for just the aerostructure, which again includes irrigation by field. And so now we could explore the fixed effects. And so I've done that here, where I'm sticking with what I believe is the best aerostructure, and then I'm going to explore all these different predictors, including the three-way interactions and all the two-way interactions. And we go ahead and we do that, and then I can say step, my fixed superfat model, oops, do that again, okay. And it goes through, and now we're just dealing with the fixed effects, and we end up with the exact same model that we ended up with when we just threw the superfat model into that step function. So again, it's telling us that we want all the predictors to be in there. We also want the interaction between irrigation and density, and we want the interaction between irrigation and fertilizer. And our aerostructure is going to be one where each field is going to have its own intercept and slope associated with the effect of irrigation. And so this then will be our final fat model. And so I can go ahead and I'll just cut and paste this. And I'm going to call this the final mod, which is going to be an Elmer, where that's what I cut and pasted in there. Make this look a little prettier. There we go. And what is the data called? Data equals yields. Okay, notice we did not get a warning. We got no singularity problems. We have our final model. We have parameter estimates from our final model. So we could do the same trick that we did when we played around with factorial type designs before. We could look at the dummy coding that's involved with that, and we should be able to come up with a predicted value for each of those. And then finally, we could go ahead and we could do the ANOVA on our final mod. Looks like that. Okay. There's the hypothesis testing part. And then just as we did before, when we notice that there's this significant interaction term, what that's telling us is that we can no longer trust the hypothesis testing for the fixed effects alone. And so what we'd want to do is a follow-up, and we would want to split those into separate models. So we would run this exact same procedure then, only looking at high irrigation or only looking at control irrigation to understand what the effects are on density and fertilizer. And of course, you know, we used the Elmer test version of ANOVA here. We could also have used ANOVA, capital ANOVA from the CAR package, which will do that modification of the likelihood ratio test. And there it is right there. Again, it's telling us that these significant interaction terms are there. And if we were really, really motivated, we could have done it as a bunch of likelihood ratio tests, because what I could do is I could say, I could have my final mod with, let's say, no irrigation by fertilizer. And so I could go ahead and I could drop that one little interaction out right there. And now if I were to use the lowercase ANOVA function and given it two models, it will know that we want to do a likelihood ratio test. And what's that telling us? It's telling us that the full model, the one that includes the interaction term, is significant. So that's its way of telling us that it's a significant interaction term. Obviously, doing it as a bunch of likelihood ratio tests can become very cumbersome, because then you'd have to do it for all possible combinations of models to find out what the best model is, which is why that capital ANOVA function is nice. Final fat mod. because it's basically doing that for us behind the scenes so that we don't have to deal with all those typings. And then again, we could do it in the more traditional one. Is that, and you know, again, we have our associated p-values for our hypothesis testing. And so again, what we would do then at this point, I'm not going to do it now, but because we've done it before, but now we'd want to separate the model into two separate models to understand what's driving that interaction term. Our parameters are fine. The hypothesis testing is the part that is suspect. Okay, so now what we've done up to this point is we've learned how to set up our error structure, and we've learned how to partition our error structure both by allowing different intercepts across each of our experimental blocks. In this case, the experimental block is field, and we've also explored models where we've allowed the slope to vary across those fields. And so that is the initial introduction to mixed models. What we'll do following this is think about different ways in which we can use mixed models. And again, it's going to be an example of where things will have a different name, but it's really the different names such as nested designs or repeated measure designs, where that's really all about the experimental design. The analyses are going to be entirely consistent with what we've been doing right here by putting some structure to our error. Hi folks, welcome back again. I'm going to talk a little bit more about what we can do with mixed models. In particular, I'm going to talk about what are called nested designs or a nested ANOVA. Again, as I've said before, it's a linear model, and we're probably going to use some semblance of an analysis of variance to analyze that model. But it's going to be similar to what we were doing when we were playing around with random effects before with a mixed model, in that we're going to want to keep track of the error structure, and we're going to want to put some structure to the error term for the purposes of both how we're going to estimate our parameters and doing our hypothesis testing. And so I've uploaded some data, and before we talk about exactly what a nested design is, let's just look at data from a nested design. Make that as small as possible. Hide in the corner. And so here I have this object called seeds nested. So I can read that in, and we can take a look at that. Let's take a look at this. Okay, so what do we have here? The scenario with this kind of a design for this example is that there are 4 different populations that we're interested in, cleverly called Northville, Midville, Weston, and Easton. See what I did there? And what we'd like to know is we'd like to know whether or not the mass of a particular species of plant, whether or not the seed mass varies among these different populations that we've identified. And so from each population, we took 5 seeds from each of 5 families. And so this is what we mean by a nested design, because what do we have? So if I were to just look only at Northville here, okay, so within Northville, let's say that that's Northville. Okay, within Northville, we took 5 different families. So 1, 2, 3, 4, 5. Okay, so this is family A, B, C, D, and E. And then within each one of those, you can see here, so for family A, we have what? We have 5 different measures of seed mass. So we've taken 5 pieces of information from each family. And so here's our seed masses. Okay, and so this is what our experimental design is. And this is why it's called a nested analysis. So the 5 families are nested within Northville, and then likely the 5 replicates within each family are nested within family. So here we have 3 different hierarchical levels. We have the level of population, we have the level of family within population, and then we have the individuals within family. And likewise, if we look at our data here, you know, we go to Midville, and it similarly would have 5 families in it. Here the 5 families would be family F, G, E, F, G, H, I, and J. And then within each of those, we have 5 observations, and so on and so forth. Okay? And so the interesting thing about a nested design, is, well, maybe not interesting, but certainly something you want to keep in mind, is paying very close attention to what your actual unit of replication is when thinking about estimating parameters and when doing hypothesis testing. And so if we're interested in the differences among towns, right, or among populations, we have 4 of them. We have Northville, Midville, and then we could, if we wanted to waste more time, do North or Easton and Weston. But it's that same setup, and what we're interested in is whether or not the populations are different from one another, which means that our unit of replication is actually the family. So even though we went through the effort of collecting 25 different pieces of information for Northville, in reality, we only have 5 independent observations, 5 random variables. Because all of these nested within each of these families are not independent of one another. And so this is an important thing to always keep in mind, both when you're designing an experiment as well as when you're reading somebody else's experiment. I will say this is probably the most common error I've seen in the literature when I've been looking. And I don't think it's a malicious error because, as we'll see, the default on statistical programs doesn't take into account this nested nature. We're going to have to either do that by hand or use the appropriate syntax in R, which will do both. Okay, so hopefully it's clear exactly what a nested design is and why we need to keep track of the non-independence. So let's go ahead and make me small again. Make me disappear. Okay, and so let's start with making a bad model, because why not? So I'm going to call it a BM for bad model. And it's going to be a linear model where seed mass is going to be some function of population, because again, what I want to know is whether or not there are differences among populations. And then the data equals my ND there. So I go ahead and I run that. And now let's go ahead and let's load in that car package. Library car. Okay, and let's do an ANOVA on that. ANOVA, my bad model. And what do we have here? Ooh, it's significant. And again, this is often how people get themselves into trouble without paying attention to the nesting structure, because we know that there's only 5 observations in Northville, there's 5 observations in Midville, 5 observations in Weston, and 5 observations in Easton, which means at most we have 20 independent pieces of information. Okay, so we would start out with 20 degrees of freedom, and as soon as we estimate the mean, now we have 19 degrees of freedom, so on and so forth. But notice what the output here, because we didn't tell it to pay close attention to the structure, we have 96 degrees of freedom in the error term, which is clearly wrong, because the most we could possibly have would be 20, and that would be if we didn't even calculate the mean overall, right? There's only 20 independent pieces of information, yet our model is saying that that there's 100 pieces of information, which isn't right. And so we could try to fix this using the linear model function in R, and we could ask R ever so kindly to treat that as being nested. And we can do that by saying we want to include population in there because we're interested in the differences among population. But then what we're going to say is we're going to say that families are nested within population. And so how do we do that? We would say plus, and then I would say population, once again, population. And then I would say family. Okay, so this is the kind of code I could write it. This is the traditional older way of setting this up, both in R as well as other programs. And so if I go ahead and I run that, now let's do an ANOVA on that particular bad model. Okay, so now at least we're docking ourselves a little bit more degrees of freedom here in the denominator. indeed, we have, we have four populations. So we have exactly what? We have four populations. We have 3 degrees of freedom across populations. And then family nested within population, we have 16 degrees of freedom. That's because we started out with a total of 20 families and we had 4 different populations. So there's 4 different means that we calculated, right? So it's the total number of degrees of freedom at that level minus the number of parameters estimated. We estimated 4 means, and so we have 16 degrees of freedom there, and then we have the residuals. Okay, so this is the part where the most frequent errors occur when people are analyzing these kind of models, because it looks like this model is working fine. Notice here that it's saying that it has these alias coefficients. It's just kind of giving you a warning. The reason why it's giving you the warning is because of how the dummy coding is working in the background. It's not falling apart, but it's just letting you know that not every family was in every population. And that makes sense. Family A is only in Northville. Family B is only in Northville. It can't be in both places. As a side note, if you are ever doing these kind of analyses, it's really important that each family gets its own unique name, because the computer, any kind of computer you use, if you recall, or if you name one of the families in Midville A, if it's always family A through E across these populations, the computer is not going to know that that family A is not the same as another family A from another population. So just make sure that you always have unique family identifiers for those things. Okay, so the reason why this is a very common error in the output here, if we look over here, is that the computer is always using the residual sums of squares as being the denominator. And so when it's calculating the F statistic. And so if we were to look at, say, how it's calculating this F statistic here, right, the 28.5 that's associated with population, what it's doing is, what do we need to do? We need the mean squared for 634.19. We need the mean squared for population, which is that. And then we're going to divide that by, and let's start with the total, right? The residual sums of squares. So that's what? That's 593.34, and then divide that by 80. That's where it's coming up with that number, okay? But that's not right, because remember that when we're using these F statistics, we're thinking about the component of the variation explained by a certain part of the model. And here, the residuals here that's all the data, but that's not the independent observations we had for the hypothesis testing part, because we only had 5 per population. And so with a hierarchical model, what we want to do when calculating the F statistic is to use the mean squared of the next nesting level. And so instead of calculating our F by taking the mean squared, in this case population, divided by the mean squared error, what we're going to want to do instead is to calculate that by saying the F is going to be the mean squared of the population divided by the mean squared of family nested within population. Okay? And so we can go ahead and we can do this by hand. Again, this is not something that you would probably ever do, because as we'll see, there's much easier ways to do these things. But let's go ahead. Okay, so that still is going to be our mean squared for the effective population. And then what we can do is we can divide that by 276.72 divided by 16. So that's going to be the mean squared associated with this level. And so we go ahead and we do that. There is our new F statistic. And so now if we wanted to get the correct p-value for that, we would use what? We'd use the cumulative distribution function for an F. We'd give it the value, which is 12.22 something something something. Yeah. And then we, where am I? 3 and 16 degrees of freedom, lower dot tail equals false. That should, where are we here? And there we have it. There is the actual correct p-value. It's still significant. We would still reject the null, the null and accept the alternative. But you can see by staying honest with the number of degrees of freedom and being aware of how your experiment was set up, you can see that we went from a very high F value, 28.5, with a p-value of times 10 to the negative 12, to now a lower F ratio with the appropriate degrees of freedom. Although still significant, it certainly isn't times 10 to the negative 12. It's 0.0002. Still pretty small, but it's different. Okay, and so that's kind of a traditional classic approach to dealing with these types of hierarchical or nested models. And it's often, I'll point out when thinking about experimental design, it's often really tempting to say, oh, we're going to do this nested design because it's really, really powerful. And a lot of times the reason why it's really powerful is because the ANOVA is done incorrectly. In particular, it's because they're using the error mean squared as opposed to the mean squared at the appropriate hierarchical level. And so we really only have these 5 observations. We don't have 25 observations. If I were running this study and if I were designing this study, I would say, why don't we go to each of those 4 populations and randomly select one individual from 25 different plants, different families, instead of having it in this nested structure, because we're doing a lot of work, but we're not getting nearly as much information. There are times when a nested design makes sense or when we have no choice but to do a nested design, but don't fall into the trap in thinking that it's a very powerful design, like it's some kind of a magical panacea, because it's really not. And we can prove to ourselves that we're not losing, we're just not accounting for all of this information in there. What I'm going to do is I'm going to create new data really quickly, just to kind of point out how this all looks. Okay, and what did I do here to make this new data? I'm using this function called aggregate. Aggregate is just a way that you can kind of summarize different parts of a data frame. What do I want it to aggregate? I want it to do something with seed mass, and I want to have family within population, and I want it to give me the mean. And then this is the data that I'm using. So basically what this is going to do is this is going to give me the mean for each family. And so here's, Northville family A, that's the mean of its seed mass. So that's the mean of those 5 values that were up here. So the mean, here's the raw data. The mean of those 5 numbers oh, this isn't me. I want ND. Where am I? There I am. The mean of those 5 numbers for family A, so 1922, 1911, 23, the mean for that is 19.02. So now that is the data. So remember, we started out with 100 rows of data. We felt as though, hey, we're going to have a lot of statistical power because we have that. But now I've just said, I don't care. I just want to take the average of that. So let's make a model where we just do that. So I'm going to just call it mod summary. No, mod mean. That makes more sense. Mod mean. And so this is going to be a model where we're just looking at the means. And so what I'm going to say is it's a linear model where what? Where seed mass is some function of population, and the data equals new dat. So now I have a model, and let's go ahead and do an ANOVA on that model, on that mod mean. And that's the answer to that, right? So this is when we just did it on the averages. We got rid of all of that extra information about all the within family variation. We just took the average for each family, and that became the response variable. What I want to point out is, first of all, we're getting the appropriate degrees of freedom, okay? We are getting the exact same F value that we got when we did it by hand, and we're also getting the exact same P value that we got when we did it by hand. And so this is just another way of just reminding ourselves that that's all nesting is. So it's not really often worth your, it would not be worth your while if you were to do this sampling design and say, we're going to take 5 families, but let's take 100 seeds from 5 families. Because at the end of the day, you still only have 5 experimental replicates. Okay, and so let's think about how to set this up as a mixed model, because it is 2020 after all, and for all the things that 2020 has become to us, one thing is true: we feel better about mixed models than we did 20 years ago. So we're going to use our friend, the library, I'm going to call in the Elmer test library, and so that's going to allow me to do the to set it up as a mixed model and be able to use, if we were doing a more complex model, we could use the step function or whatever. But I'm going to go ahead and let's make a model, and we're going to make a model using Elmer, so setting it up as a mixed model. And so it's going to be a mod. That mod is going to be an Elmer, where I'm going to have seed mass is some function of population. And now I'm going to add my random effects into the model. And what are those random effects going to be? The random effects are going to be each family. So we know that all of these pieces of information within family are not independent from one another, that it's only among families where there is independent information. So what we're going to do is we're going to allow each family to simply have its own intercept. And that's going to be the way that we're going to control for this nested by, essentially, what are we doing by doing that? We're treating family as a random effect. And it might make sense that you'd want to think about family as a random effect because they're just 5 families drawn from a potential distribution of families. So let's go ahead and let's set it up as we did before as a mixed model. So one pipe family, what that's doing is that's telling the Elmer function that we want each family to have its own intercept. And then our data is our nested data that we were playing with before. Okay, so now we have a mod, okay, and we have parameter estimates for each population. And we can go ahead and do an ANOVA on our mod. Recall that when we load in the Elmer test package, if we use the lowercase ANOVA function, that function knows, since it's an Elmer object, it knows what it wants you to do with it. I don't know why they didn't at least do what CAR did, which was have a capital A versus a lowercase a. They could have done like maybe a ANOVA with a capital V. I don't know, but they didn't. So just be aware of that. So I'm going to go ahead and I'm calling up this ANOVA function. And we're going to look at the mod and look at that. That is the exact same answer that we got when, if we go back up here, when we did it on just the mean. Right? Remember when we just took all of those values within each family and we just took the average of all those individuals? That is the exact same answer that we got when we did it that way. So here it is setting it up as a mixed model. Here it is doing it as a traditional linear model. But instead of including the error for family, we're just taking the summary of the family and going along, and just going away with it. So it's actually a lot easier to set it up that way. But we want to do things complicated because it makes us feel smart, and so we'll set it up as this type of a mixed model. Now, obviously, you could also have done the hypothesis testing a number of different ways, right? So we could do it as, I'm going to say mod reduced, and what I'm going to do is I'm going to say no population in there. And now if I used ANOVA, but I gave it 2 models, mod and mod reduced, now it's doing it as a likelihood ratio test, which we've also done before, right? So here you would say, yep, population is significant, here's the p-value, okay? And then finally, the way that we could do it is to use the capital A ANOVA and put the name of our model in there. And then it's going to do that analysis of deviance, that other approach to doing likelihood ratio type statistics. Right. And so that's it for nested designs. They can get tricky. I often encourage people to really think hard if they truly think that they want to do a nested design. Because again, your unit of replication depends on what hierarchical level is relevant to your hypothesis testing. And since we are interested in their differences among populations, that means family was our level of replication. And we only had 5 observations from each of those 4 populations, as opposed to, even though we measured 25 things. So just be aware of that. But for the most part, yeah, that's it. Some places where nested designs are still frequently used are things like in quantitative genetics, when you're trying to estimate heritability and you're actually interested in the amount of variation within versus among families. And in those types of situations, a nested design might be appropriate. A lot of times you have no choice but to end up with a nested design just because of the reality of your experiment, right? If these were, these are seeds in principle, if there were only 5 trees in each of these populations, you wouldn't really have much of a choice but to take multiple samples, even though at the end you would only end up with 5. And so, again, the better experimental design here might be 1 seed from 25 different plants or 25 different families, as opposed to 5 from 5. Yeah. So, okay. So that is what nested designs are. The last one that we'll talk about next time is a variant of a nested design, and it's what's called repeated measures. It'll be very exciting. Okay. Hello, everyone, and welcome to the last installment of thinking about mixed models. And this will actually be the last time that we'll explicitly be thinking about general linear models or general linear mixed models as we know them. What we'll get to starting next week is start thinking about totally different types of error structures instead of thinking about normal. So today we're going to finish up and we're going to talk about something that is called, historically it's been called repeated measures. And again, this is really about the experimental design more than it is about the modeling approach. Repeated measures, as the name implies, refers to situations where you are taking repeated measures from the same subject or the same individual or the same plot. So in some ways it's, and as we'll see, it's very similar to how we set up the models when we had a blocked design. Or even a nested design. This is just a different name for the same type of modeling situation where we're going to want to make sure that we're paying attention to the degrees of freedom when we're doing our hypothesis testing and also estimating the uncertainty around our parameters. And so I've set up and I've cooked up, as I'm wont to do. Let's make me small. Bye, Jim. I've set up this scenario here where I just have some cooked up data, and let's just look at it and we can explain it. So what do we have here? We have an experiment where we measured something. We have 4 different treatments. We have a control treatment, drug A, drug B, drug C, and then we have subjects 1 through 10. So in this scenario, there were 10 people that were involved in this study. Each of those 10 people received all 4 of the treatments. So you could almost think about this as being a blocked design, except there's no replication within blocks. Each subject, so person 1 here, only 1 time received the control treatment, 1 time received the drug treatment A, drug treatment B, drug treatment C. So one important thing to kind of point out with repeated measures designs is that there's often this idea that the repeated measure has to do something to do with time. So early, mid, late, for example, if you measure the same individual, that would be something that oftentimes people would analyze as being something from a repeated measures design. There is nothing in the repeated measures itself, or at least the analyses for repeated measures that we're going to talk about, that explicitly accounts for anything to do with time. But you often see that in a lot of statistical programs where by default they're going to assume that that repeated thing that you're doing within subjects is some measure of time. And again, the modeling is not going to take into account time as being an ordinal thing, where time 1 comes before time 2 and time 2 comes before time 3. And so don't worry too much about thinking that it has to be about time. Actually, in a perfect world, like with our example here, where we have each subject is getting the 4 different treatment combinations, in a perfect world, you would randomize that for each subject. So maybe one subject would first have drug A and then drug C and then drug B and then control, and maybe somebody else would start with control and then B and then C and then A, and so on and so forth. So I just wanted to mention that because a lot of programs like JUMP and a few other statistical programs, it just assumes that you're doing stuff with time. And again, that's not an uncommon thing for people to use, a repeated measures design, when they are measuring the same thing at multiple different time points. But I just don't want you to think that it has to have anything to do with time, because actually formally it has nothing to do with time. Okay, and so here are our data in long form, and we could you could imagine that maybe we would be tempted to just analyze this if we're interested in a difference of our response variable across these different treatments. It might be tempting to set up a linear model where y is some function of our treatment. So it might look something like that. We have our parameter estimates, and we have some estimate then of the effect of drug treatment A and drug treatment B and drug treatment C, all versus the control. The control would be the intercept. So it looks like all of these different drugs, there's an increase in the value of y compared to the control group. But if we were to do an ANOVA on that, let's go ahead and do that. What we see is, first of all, we might have a big sad face because, oh, nothing significant. That was a lot of money and we didn't learn anything. But more important, we could look down here at the degrees of freedom, and immediately we should recognize that there are far too many degrees of freedom in this model for hypothesis testing. We only have 10 individuals in the study. So we need to account for the fact that really we have 10 experimental units in the study, and each of those experimental units received all 4 of the treatments. But when we ran this analysis of variance right here, it was not accounting for the fact that we only really had 10 experimental units. And we can set up the data a different way just to see just to kind of drill into our heads that this is individual 1. This is the response for the control, drug A, drug B, drug C. This is individual 2. Drug A, drug B, drug C, so on and so forth. So you can see when we set up the data this way, there's only 10 rows of data, and that's because we only had 10 experimental units. We only had 10 people in this experiment. And these kind of things are actually quite common in like the biomedical literature and things like that, because it's very expensive to maintain laboratory animals, and especially if it's trials that are done on humans, it's very expensive and very difficult to get the permission to do any kind of an experimentation on humans. And so you generally wouldn't be able to have the perfect design that you might want, which would be, you know, let's get 1,000 people and give 250 one thing, 250 the other, 250 the other, 250 the other, and have truly 1,000 independent observations. That's just not going to be realistic with the limitations of a lot of experiments. Okay, so that's what our data looks like, and we know that this ANOVA then is what we might think of as incorrect. And then again, we can maybe be sad about, you know, why are we not detecting any difference? And so what I can do is I'm just going to make a plot here so that we can plot out our data and kind of understand what it's looking like. So this is just the raw data that I'm plotting here for the control group, treatment A, treatment B, and treatment C. Okay, and you can see there's a lot of spread in these points, and so maybe it's not entirely surprising that we failed to reject the null hypothesis if there was any difference, just because there's so much variance there. We have very little power to detect what would relatively be a small effect size. And we can again remind ourselves of what the hypothesis testing was doing when we set up that ANOVA. There's the grand means for A, B, and C, and you can see that they're all pretty much right on top of one another. So again, it might not be terribly surprising that we fail to detect an effect. What we could also do is we could look at it using the interaction plot function, which I was trying to sell you guys on because I just think it's so neat. Where we have treatment, we have subject, and we have our response as y. There it is as an interaction plot. There's all of our different subjects. And you can see like subject 9 overall is just higher than the rest of them. So what we want to do is we would like to remove all of that among subject variation when we get to the point that we're going to do hypothesis testing. Okay, and again, here's those means. And so again, it's not terribly surprising that we might not detect an effect. So by putting structure to the error and removing the effect of among subjects, now we're going to be able to remove that, and then we can think just about the variation that is explained by the drugs. And so for conceptual purposes only, and the code is included in the R scripts that I've given you, but I put in large, big exclamation points. This is only for conceptual graphing purposes. But what I'm going to do is I'm going to take each of these individuals and I'm going to center them around the mean. In other words, the mean across all the different treatments for each individual is going to be 0. And that's the way that I'm going to just for visual conceptual purposes, remove all of that among individual variation. And so what I'll do then is I'll have a plot where I have it centered now at 0. So I expect the mean of each subject, of each individual in the study, I expect the mean across all 4 treatments to equal 0. And we can go ahead and we can plot and see what that looks like. Okay. And so now you can see that, well, now it does look like the control is a little bit less than group A and B, and then C is up here a little bit higher. So just by centering things, we're now able to visualize that there actually is a bit of a difference there, and that's because we've gotten rid of that whole effect of, whoever it was, individual 9 up here being way higher than everybody else, and then individual 8 being really low. What we want to do is we want to just remove the effect of all that among subject variation. Right, okay, so let me, I'm going to change this new data into a long vector. And so that's our centered data now. And I'm going to go ahead and I'm going to do an ANOVA on a linear model where my new data now, which is the centered data, because again, we're only doing this for, you will never do this, I hope, treat. But we can understand then, now this is doing the analysis on the centered data. So we've transformed our data by centering it for each individual. And we go ahead and we do that, and I get the same annoying warning messages I seem to always get. And so now we look at this and, well, the p-value is significant now, which it wasn't before, so that might make us feel good, but we should still not feel too good about this model because we still have 36 degrees of freedom in the model. And that's because we're running the analysis on those data, but we're not accounting for the fact that we've already estimated 10 parameters in order to center that data. The only way that we could have centered that data would be to calculate the mean of each subject. And so what we want to calculate then is the correct degrees of freedom. And we can do that by saying, all right, what are we starting with? We're starting with 40 total observations. Okay. We're going to lose 3 degrees of freedom because we have 4 different treatment groups, right? And it's always the number of parameters minus 1 is going to be the degrees of freedom for the model part of our model. And that's because the intercept is sucking up the control group, and then we have those 3 parameters that are a reference to that. So we're going to say 40 minus 3. And if I were to do 40 minus 3, yep, that's fine. And then I'm also going to always going to lose 1 degree of freedom because at some point I had to calculate the grand mean in order to figure out the sums of squares. So this is the same as when we did any kind of multiple regression. And sure enough, if I run 40 minus 3 minus 1, I have 36 degrees of freedom in the residual, which is the exact same thing I got up here in that model. Okay, so we know where that comes from. But again, the one thing that we haven't accounted for in doing all of this is that we've already estimated a bunch of other means when we did the among individual component of the variation. And so we estimated 10 means, 10 parameters, 10 minus 1 is 9. So we're going to additionally remove from this 9. Nope, that's 6. That's a 9. There we go. Okay, so in principle now, that should be our correct degrees of freedom, which means that if we wanted to calculate the correct mean squared for the residuals, we would take the sums of squares associated with the residuals, but now we're going to divide it by 27. Okay, so that is what our appropriate mean squared should be for the residual term. And we can remind ourselves, it's always good to remind ourselves where this f value comes from. And again, we're using the f value to do the hypothesis testing because it's a variance component problem. And so that f value, again, comes from the mean squared of our model divided by the mean squared of our error term. And that's where we're getting that 8.1225. But again, this is the incorrect mean squared because the degrees of freedom here are incorrect. This is the actual correct mean squared that we want. And so let's go ahead and pop that in the model. That is our correct F ratio. That is the F ratio that we would potentially want to use to do hypothesis testing. And we can even take that F ratio and put it into the cumulative distribution function for an F. So it's going to be that, and there's going to be what? 3 and 27 degrees of freedom, and lower tail will equal false. And then here we have 0.002644282. That is the correct p-value, as long as we're happy that that's the correct way to calculate the denominator degrees of freedom. And so clearly you would never do this by hand. I only went through this exercise so that everybody would understand what the consequences are of adding that structure to the error term. We're removing that among subject component of the variation, and we're not using that as the denominator when we're thinking about what portion of the variation can't we explain, because that's where our statistical hypothesis testing is going to come in. So there's a couple of different ways that we can approach this. I'm going to just set it up as a mixed model approach. I will mention that in older literature, and by older I mean even literature that's only 15, 20 years old, which I'm sure to you guys sounds pretty old, but to me it just makes me feel old, is that people used to analyze a lot of these types of models using what's called a MANOVA, which is multivariate analysis of variance. Multiple analysis, yeah. It uses a multivariate normal. People don't really do that anymore, so I'm not going to really talk about that. It's again one of these things where I wanted to mention because you might find older papers where people are in principle doing a repeated measures design and they're giving you output that is entirely new and unfamiliar to you. But people don't really do that much anymore, and I think it's because they don't really feel comfortable about the underlying assumption of what's called multivariate normality. And the accepted way that people like to deal with it now is to set it up as a mixed model. And so I'm going to do it two slightly different ways. First, I'll do it not explicitly as a mixed model using that Elmer package, but I'm going to basically redo what we did right up here. If you recall, there was that AOV function which we had to use for one of the post hoc tests, I believe, where it's another way to keep track of all of the information that's in an analysis of variance, but it doesn't explicitly give you the hypothesis testing at the end. And that function was called AOV. So I'm going to create an object called AOV out, and I'm going to say it's an AOV. And I'm going to say that y is some function of my treatment, so that's consistent with what we did before. But then what you can do in the AOV function is you can be explicit about your error term, And then what I'm going to do is I'm going to say that subject is, that treatment is nested within subject. So that's what that syntax is telling R. It's telling me that I do indeed have an error term. You're always going to have an error term. But in this, for this particular error term, I'm going to assume that each treatment is nested within each subject. So I can go ahead and I'll do that. And now if I take the summary of that AOV out, I want to point out that, okay, it's telling me what's going on in the error term. There's that degrees of freedom that we thought about. There's 10 different means. Number of parameters was 10 then. 10 minus 1 is 9. That's how many degrees of freedom are associated with that one particular part of the error term. And then here is the hypothesis testing part. And what you'll note here is that this is the exact same mean squared we got when we did it by hand. And this is the exact same F value we got when we did that by hand, which was there. And then again, we did the same p-value. And so this AOV method, which is really kind of the older school method, but as we'll see, it really doesn't matter, of dealing with this, is the exact same answer as we got when we decided, you know what, let's center all of our data, let's cheat and just do that on the front end, and then just keep track of our degrees of freedom. By explicitly telling the AOV function that we want to put structure into our error term, it's doing the exact same thing. Okay, so now let's welcome ourselves to the early 2000s, which just seem to be doing great for us at the moment, and set it up as a mixed model. And so I'm going to go ahead and I will load in that package. I'll go ahead and load in Elmer test. And I'm going to now make a mod. And so let's think about how we've set up the other mixed models. And this is going to be the same underlying philosophy that we're going to do, is that we're going to assume that each subject is different from one another, right? We know that one subject 9 was way up there and subject 8 was way down there. And what we're gonna say is that we would like each subject to have its own intercept. And again, that's just our fancy way of saying I really want to put error to I want to put structure to the error term. And before I do my hypothesis testing and my parameter estimation, I want to remove that component of the error or the residual that I know that I can explain that portion of the variation. So it's the part of the error that I can explain, so I don't want to treat it as the unexplained part of my error. So it's the exact same thing that we did when we did the block de novo, which again was just a linear model with the organized error structure, and the exact same thing we did when we did a nested de novo, which again is just a mixed model. Okay, so let's go ahead and let's do that. So I'm going to say that my model is going to be an Elmer, where y is going to be some function of treat. And then I'm going to say I would very much like it if each subject got their very, oops, probably should spell that correctly, if each subject got their very own intercept. So I go ahead and I do that. And now I can look at the summary of my model. Okay. And so again, we have the same kind of standard output as we had before. I'll just look at this variance component. Recall that we can say, well, how much of all of that variation that we couldn't explain in our model, how much of it was actually because there was just all this among subject variation? And we could do that by just saying, well, what fraction is our subject variance versus all the variance? And what do we have besides annoying error warning messages? 98%. So that means when we set it up as kind of a traditional linear model and we ignored all of the non-independence of the experiment being done within each subject, if you recall, it was not significant. And I jokingly said, oh, we have a big sad face. Here it is right here, right? So even though we got more degrees of freedom, we are still getting a really high p-value, meaning that we're unable to detect an effect. But that's because, again, when we're doing the hypothesis testing, we're looking at the ratio of the error term versus versus what we can explain with our model. And we have a lot of variation in the error term because there's a lot of among subject variation. And in fact, 98% of that variation in the error term was due to among subject variation. And so by removing that, now we have relatively a small amount of error that we're unable to explain with our model. And so let's go ahead and we can run the ANOVA on that. And then here we have it. Look at that. We get the exact same answer as we got when we did it as an AOV. And we would get the exact same answer if we went through Jim's long convoluted way of centering all the data and then calculating the F statistic by hand, which again is something you shouldn't do. But hopefully if you rewatch that part once or twice, you'll totally get what this is doing behind the scenes, which again is removing that part of the variation that we don't care about when it comes to hypothesis testing. If we're interested in how the drugs are different from one another, I don't care that subject 9 was much larger than subject 8. What I want to do is I just want to remove all of that variation, and that's what we're doing here. Okay, and so we could follow that up then. Oh, I do want to remind everybody that when we're doing the ANOVA here, and we're getting this output, that's because we are using the package called Elmer test, and Elmer test is assuming that we know the appropriate denominator degrees of freedom. And there still is an active argument in the community about whether or not that is the appropriate degrees of freedom. And we could even look at what the output would look like if we had just used the LME4 package, which was the very first package that we started playing with when we started doing these models. And so I can do that. Let me call this LME4. So this is a way in R where I can say I don't want to use Elmer test's version of Elmer. I want to use the version of Elmer from LME4. And again, there are two functions that are called the same thing, but Elmer test overwrites the version that's in LME4. And I apologize if that's confusing. I'm not the one who wrote the packages. But this is using, if we just use LME4, and then if we were to do an ANOVA on this, I just want to remind you that we wouldn't get a p-value. We would still get the same mean squares, we would still get the same sums of squares, we'd still get the same f value, but we would not get a p-value. And the reason why we wouldn't get a p-value is that the original authors of the LME4 package decided that they were going to be conservative and not get in arguments with people about what the appropriate denominator degrees of freedom are. Again, either method is entirely valid in the current state of the art in statistics today. As I think I've mentioned before, in statistics, there's no one right way to do something often. There's clearly lots of wrong ways to do something, but there's no one right way. And mixed models is a really good example of there not being one accepted right way. But if we were to stick with this LME4 object, we could again use, let's open up the CAR package, and if we were to use the capital A ANOVA on that, we would get this walled chi-squared test. And we could likewise take our object that was made in the Elmer test, and we would get the exact same answer. So the capital A ANOVA doesn't care whether or not you use Elmer test or whether or not you use LME4 when putting together a mixed model. And then of course the last way, let's just make sure that we are all good here. We could also create a reduced model. I'll call it .r, where all we're doing is estimating the error. And then we could compare that reduced model with our more complicated model, and there would be the associated p-value with that. What that's telling us is that the model that included treatment is a better model than the model that didn't include treatment. So again, here's the three kind of standard ways in which we can do hypothesis testing on such a mixed model. We can either use the Elmer test function, which does it in more of the traditional way, where we assume that we know what the appropriate degrees of freedom are for the denominator. We can do it as a likelihood ratio test, which is what we've done right here, or we can do it as that other variation of it, that walled chi-squared test, which is just another kind of flavor of a likelihood ratio test. And then I guess finally what we could just really briefly revisit is we could find out where those important differences are. So up to this point, what do we have? I gotta find the name of the library or else I'll get lost. It's library multcomp. That's what I wanted. So we can now do post hoc tests and ask where are the important differences, because all we've done thus far is we've done a really good job at, first of all, modeling it correctly, where we have the appropriate, where we can do the appropriate hypothesis testing and conclude that indeed there is a difference somewhere between the control group and treatment A, treatment B, and treatment C. And so we could use the multcomp package. And we could start with, if we wanted to, we could do a Tukey's HSD. So that's the standard standby that people seem to like for doing hypothesis testing. And we're going to do it on our mod. And then what are we going to do? We're going to do these multiple comparisons where treat is going to equal, and then we tell it that we want to do a Tukey test. Right? So it's just like we did when we did just standard post hocs with ANOVAs. And so there's that. And then if I were to take the summary of that, we can now look at where those differences are. And so it looks like control and drug A are different from one another. If we are dead set on our alpha of 0.05, drug B is not different from the control, but drug C is different from the control, and we're not detecting any differences among the different drugs. There's a pretty good chance if we were actually analyzing these types of data that the Tukey probably isn't the most appropriate test to do, because, well, it might not be the most appropriate test to do, because we might just be simply interested in whether or not any of these drugs are better than the placebo, than the control group. And if we wanted to do that, then we could set it up as a Dunnett's test. And so let's go ahead and create an object called Dunnett's. Oops, spell it right. And then here in parentheses, we're going to tell it that we want Dunnett. So remember, what Dunnett is going to do is it's going to take your first factor level and it's going to compare everything just against that. Because of how I've put in these the names of the different treatments, control starts with the letter C, which means that it's going to come before drug A, drug B, or drug C. So we're going to compare everything only against the control group when we do this. And we'll go ahead and we'll do that. And now notice that they're all showing up as being different. It's a more powerful post hoc test because we're doing fewer comparisons. And the fewer comparisons that we do, the more statistical power we're going to have to detect an effect. So if we had set it up as a Dunnett's contrast, then we would say all the drugs are better than the control group. And then we could, interpret our effect sizes. And, on average, it looks like drug C is the best. It's 0.44 greater than the control group. It's almost twice as good as drug B compared to the control group. And again, that's all just about how we're choosing to interpret our hypothesis testing at the tail end. Okay. And so again, that ends up that finishes up looking at putting structure to our error term, and that's really what mixed models are all about. And hopefully, if you go back and you kind of focus in on the blocked design, the nested design, and the repeated measures design, you realize that all these models are essentially doing the same thing. Basically, we're keeping a close eye on what our true experimental units are and what the appropriate level is for us to do the statistical hypothesis testing. And so in the blocked ANOVA example, we simply tried to remove the variation that was due to among block variation in order to do our hypothesis testing. When we did it as a nested ANOVA, we wanted to account for the non-independence of the observations within a particular hierarchical level. So whether it be 5 seeds from a given plant, for example, we wanted to account for the non-independence of that. So we allowed each plant to have its own intercept. And then here in this example with the repeated measures design, again, you can think of that as just simply being a blocked design, but there's no replication within blocks. And then we're setting it up the same way. We're going to allow each subject to have their own intercept. So not only by doing that are we modeling things appropriately, which is always nice to feel as though you're modeling things appropriately, you are also accounting for the fact that you can actually put some structure into that error term, which in principle should increase your statistical power to make inferences where maybe you can decide that certain things are important or are not important for your response variable based upon the parameters in your model. So on that, I will say have a fantastic couple of days. And what we will start on next week is we will start on what are called generalized linear models, where again we're gonna push all this normal stuff to the side and do things that are maybe more appropriate if you have different types of data. So we'll start next time by revisiting our friend the binomial distribution, which I'm sure everyone has missed a lot because it's been months since we've talked about the binomial, and don't want the binomial to feel lonely, so we'll revisit it. Okay, cheers.